Welcome back, students. In this section, we are discussing about the image formation by spherical lens. First, we can consider the image formation by a convex lens. In case of a convex lens, it is possible to place the object or consider the object at 6 different positions in front of the lens, and in each case, different types of images are formed at different positions. That is, in case of a convex lens, we have to consider 6 different cases of image formation. And which are the possible positions? First one, the object at infinity, that means very far away from the lens. Another one, just beyond the 2f1, behind 2f1. Then it is possible to consider the object at 2f1. Then between 2f1 and f1. Then we can consider the object at f1. Then finally, it is possible to consider the object between f1 and O. Okay, we can consider the first case when we consider an object at infinity. From an infinity distant object, all the light rays we have to consider as parallel one. That means a parallel beam of light rays we have to consider. In order to obtain an image, minimum 2 light rays is enough. So we have to consider two light rays from that infinity distant object. Then that light rays parallel to the principal axis. Then after refraction, what happens? If the light rays are parallel to principal axis, then after refraction, it moves through the focus. We can see that the light rays are intersected at the focus F2. That is, when the object is at infinity, a convex lens provides a real, inverted and highly diminished image at the focus F2. Since it is actually intersected, that is a real image. Real images are always inverted in manner. So, if the object is at infinity, convex lens provides real, inverted and highly diminished image at the focus F2. And the second case, when the object is behind 2f1. We have to consider an object behind 2f1 in contact with the principal axis. Then from the topmost point of that object, we have to consider 2 light rays. Here, first one we can consider the light ray moves parallel to the principal axis. Then after refraction, what happens? It moves through the focus. And second one, we can consider the light ray which is passing through the optic center, or the light ray which is directed towards the optic center, that moves without any deviation or without any change. Then we can obtain the image. That means the refracted light rays are intersected at a point and just join that point with the principal axis, that gives the image. When the object is placed beyond 2f1, the convex lens provides real, inverted and diminished image between f2 and 2f2. Between f2 and 2f2, we obtain a real, inverted and a diminished image. Then the third case, when the object is placed at 2f1. We have to consider an object at 2f1, and from the bottom point, first light ray we can consider parallel to principal axis. Then after refraction, it passed through the principal focus. Then next we can consider the light ray which is directed towards optic center. It moves without any deviation. Then here also we obtain a point of intersection and just join that point of intersection of refracted light ray with the principal axis. Then we obtain, that gives the corresponding image. When the object is placed at 2f1, the convex lens provides real, inverted and the same sized image at 2f2. The fourth case, we have to consider the object between f1 and 2f1. Consider an object between f1 and 2f1. From the top point, we have to consider two light rays. First one parallel to principal axis, then after refraction, it passed through the principal focus. Then second one we can consider light ray directed towards the optic center and it moves without any deviation. Then here also we obtain an intersecting point of the refracted light rays and join that point with the principal axis. That gives the corresponding image. When the object is placed between f1 and 2f1, the convex lens provides real, inverted and enlarged image beyond 2f2. The fifth case, we have to consider the object at f1. Consider an object at f1 and from the top point, first light ray we can consider parallel to principal axis, then after refraction it passes through the focus. And second one we can consider the light ray directed towards the optic center, it moves without any deviation. Here the refracted light rays are not intersecting at any point. When we observe in these refracted light rays, it moves parallel to each other. So, only there is a possibility of intersection at infinity. These refracted light rays may be intersected at infinity. So, when the object is placed at f1, the convex lens provides real, inverted and highly enlarged image at infinity. In the last and sixth case, we have to consider the object between f1 and optic center O. Consider the object between optic center and f1. From the top point, we can consider first light ray parallel to principal axis. After refraction, it passes through the focus. And second one, we can consider the light ray directed towards the optic center. It moves without any deviation. And here, when we observe the refracted light rays are diverging to different directions. They are not intersecting and they are not parallel. They are diverging to different directions. So, in this case, just we have to extend the refracted light rays backward. That means, we feel that these light rays are originating from a common point behind the object. So, here it only seems to be intersected at that point. So when the object is placed between f1 and O, the convex lens provides virtual, erect and enlarged image beyond the object or behind the object. Only this is the case where the convex lens provides virtual and enlarged image when we place the object between optic center and f1. Next, we have to consider the image formation by a concave lens. In case of this concave lens, we can place the object in front of this lens at different locations, but only two types of images are formed, or only two types of images are obtaining in case of this concave lens. Therefore, in case of this concave lens, we have to consider only two cases of image formation. That means, one case we can consider the object at infinity, and the second one is other than infinity, whatever may be the position of object, the concave lens provides same type of image at the same location. So two possible cases is, first one, object at infinity, and the second one, object between infinity and optic center. These are the only two possible cases in case of a concave lens. First, we can consider the object at infinity. If the object is at infinity, all the light rays we have to consider parallel. So, two light rays we are considering parallel to principal axis. Then after refraction, these light rays are diverges and seems to be diverging from the focus f1. So here it only seems to be intersected at that point f1. So the concave lens provides a virtual and highly diminished image at f1 if we place the object or if we consider the object at infinity. If the object is at infinity, the concave lens provides virtual, erect and highly diminished image at the focus f1. In the second case, we can consider the object any other position other than infinity, between infinity and optic center. Consider an object in contact with the principal axis, and from the top point we have to consider any two light rays. First one we can consider parallel to principal axis. Then after refraction, it seems to be diverging from the focus f1. And the second light ray we can consider which is directed towards the optic center, and that will move without any deviation. So here we can obtain a virtual point of intersection. The light ray which is directed towards optic center and the refracted light ray from the focus f1 seems to be intersected between f1 and O. Just join that point with the principal axis, that gives the corresponding image. When we consider the object other than infinity in case of a concave lens, it provides virtual, erect and smaller image between f1 and O. That's about the image formation by spherical lens.